So we basically reached now the heart of nuclear astrophysics, which is the Hedgepoing-Russell diagram. And it's amazing. No, sorry, I'm figuring out here a bit where's what position on my screen. Now everything should work. So you have seen, if we take all the stars around us, take the red ones to the right, take the blue ones to the left, take the bright ones to the top, take the faint ones to the bottom. There seems to be some ordering. There is a band going from top left, and you have seen there were only a few. Bottom right, where we find much more. So we get already some kind of statistics. What do we have in big ones? So blue ones, loads of pressure in the center, high temperatures, burning fast, loads of energy produced, energy makes it to the surface, and the star gets a temperature and shines. So then we see down here group, and you have seen something going to the right and a few on the top. This is then the Hedgepoing-Russell diagram. On the left side, we have plotted the luminosity in solar units. So if we go to one solar unit, which star will have it, of course, our sun. Going here, we come to the sun, with obviously one solar mass. Then we have here our standard 5,000 to 6,000 Kelvin. So on the bottom, we have basically the temperature inversely, the decreasing temperature. We could have also, I wonder why Hedgepoing and Russell plotted it this way around. By the way, I think they did it independently, and then we just formed it at some point together and honored both. So temperature here is low, temperature on the left side is high. And then you see this O, B, A, F, G, K, M. These are classes of stars that astronomers would speak about. Since I'm too lazy to remember them, what I will talk is then about blue stars, sun-like stars, and the red stars, the red dwarfs. So blue giants, red dwarfs. So this is, and what we see is the really majorities of this band, but be careful because we have here a linear scale, but this here is a log scale. So this is basically an exponential function or dropping exponential this way around. So, and this here, this band is called the main sequence. Turns out that about 90% of the stars, or more than 90%, are found on this main sequence. So this seems to be the dominating part of the lifetime. And then older stars are found either leaving here, this main sequence, or somewhere above here. That depends now on the initial mass, whether we get giants or we get supergiants. So another thing that is plotted here is the radius of the star. So obviously the sun, and then we have here this diagonal or decreasing straight line with one solar mass, one solar radius. Then we can have a tenth of a solar radius, then we are obviously already at a very small star with maybe a few percent of the mass of our sun. And remember, there's this lower limit that the star can sustain the nuclear burning. If the pressure, the temperature is not high enough, the tunnel probability through this Coulomb wall is then basically zero. Okay, so if we go to 10 times the mass of our, this again logarithmic, or the radius of our sun, well, is Pollux, wherever Pollux is. already 10 times bigger than our sun. That Mercury might soon get problems if this happens with our sun. And then the bigger ones, it's easy even on the mean sequence, or that they are 10 times bigger. If we go to 100 times of our sun, well, we see there are these supergiants. And maybe Aldebaran is just on the way. By the way, Aldebaran is also easy to find in the night sky. Hopefully by now, everybody knows how to find Orion. And hopefully this works. No? To change to the pen. Change in color. Let's do some yellowish, that is good contrast. So if we have again, nope. Nah. Oops. Okay, hopefully for you that wasn't too disturbing. Okay, doesn't really want not to write. Pen up, highlighter in color. Okay, it doesn't work. If you take in Orion the 3 stars of the central belt and follow them top right about 10 times, you find their relatively bright star. This is Aldebaran. So relatively easy to find. Sorry that I now messed this again up. So this would be this red giant. In Orion itself, the top left star is Betelgeuse. And if you look at it, it really appears already with our naked eye to be a bit reddish. It is a red supergiant. So together with Antares, some of the biggest one, but there are stars that are even, this is now 1,000 times, almost a couple of 100 times the radius of our sun. So, boom. Big. If you take now the sun, 1 million kilometers diameter or radius, and enlarge it 1,000 times, you will be almost in Saturn orbit. That gives you a feeling, or the dimension, what then happens with the supergiants. But there are even bigger ones around. So, but obviously, most of the time, the star spends here. Then we had also established the bigger the star, the far higher is the pressure and therefore temperature in the center where the burning takes place. So the oven is hotter. And the faster it burns off, much, much faster, exponential again. It burns off the fuel. This allows us in the Hedgepoing diagram to give them the lifetimes roughly of the stars. And we see our sun is again 10 to the 10 years. What is this? 10 to the 6 would be million, 10 to the 9 is billion. So we have 10 billion years. In Canada, we find rocks which are 4.2 billion years old. If we believe that radioactive decay laws are okay for thorium and uranium, then we can say they are 4.2 billion years old. Then probably it took a while until the rock wasn't so cold that it enclosed this block material, uranium, thorium. So we can say that 4.5, 5 billion years, that's about the size, the age of the solar system. That means we are just half time. So nothing really to worry, but our sun is constantly changing. And I later talk about the burning processes, and then I will mention that the Cno cycle produces more energy. And this takes more and more over the Cno cycle. It means our sun gradually starts producing more and more energy. Will become hotter, and very likely in 1.5–2 billion years, it's so hot that the Earth on its orbit, there won't be any liquid water anymore. So global warming just on a different time scale and a different heat scale. But 2 billion years, even let it be 1 billion years. Mankind exists now. If we say it was this Australopithecus in that has been found in South Africa, 2 million years, 150 million years until before, or sorry, 150,000 years that we have left Africa, at least the Europeans. So they are now a factor of 1,000 or 500 to 1,000 in the time scale until it really the first problems with our sun start. So nothing really to worry about. So our sun will live roughly 10 billion years. And then we have said that the bigger, the shorter life, because the more fuel consumption, or the fuel consumption is so drastically enhanced. Well, if we go to, this is 1 solar mass, this here is 3 solar mass. So if we double, then we are probably already a factor 10 down. It's only 1 billion years. So if we go to 6 times the mass of our sun, we are just of 100 million years. So wherever this arc now is, so Sirius I might find, Vega I certainly would find. This is somewhere in the relative center. There's this W, and I think there it's one of these stars. So 6 times the mass of our sun, only a factor of 6. Well, and you're already from 10 billion to 100 million. Then if we go to 10 times, 30 times, obviously that's also log. This should be 20 times roughly the mass of our sun. We are down at 10 to the 7, which means 10 million years only. Basically, you switch on the star and 10 million years later. Well, what do we know about such stars that everything that has less than 1 billion years in lifetime in terms of life, at least intelligent life, can be very likely ruled out. And also, of course, what is very unpleasant, these stars emit a lot of UV light. Not the healthiest one if you want to form molecules. So again, so everything here we can almost rule out for life. If we go to the other side, and then basically if you go to 0.1, 0.3, this must be then 0.54 or 5. Only 40–50% of the mass of our sun, we are then at 10 million years, we are at 100 million years. What means 100 million years? It's perfect for us. Or if our sun doesn't work anymore, we know that the universe is 13 billion years old or 14 billion years. Why not settle over to one of these stars? Of course, the planet needs to be much, much closer towards the sun because they are much fainter, as we see here. If we have 1 solar mass and then go here over, then it's only 10% of the luminosity. We need to be much, much closer to the star in order that we get enough light to have enough heat on the planet to have how to say that liquid water exists. This is our aim. This is the habitable zone. Distance closest approach where water evaporates because it's too hot, or too far away where water is frozen everywhere. So things that we learn. Then, of course, we know that the Planck spectrum is different. It's shifted more towards the longer wavelengths, more to the reddish. Oh, I don't know which light exactly is used, whether it's more bluish or reddish in the photosynthesis. Maybe the photosynthesis works better, maybe it works less. In general, what we know from the Planck law is also that there is much less power emitted, what we had already with luminosity. So don't know how well there the photosynthesis will work. So we are relatively lucky for life that we know. It's perfect on the sun. Okay. Now what we know, we have this super, by the way, if this year is 100 billion, guess how long this year live? Maybe 1,000 billion years. So when you have only 10% of the mass of our sun, and then you go down and basically these super red dwarfs, which just before they become brown dwarfs. Brown dwarfs were these guys that are just occasionally produce a bit of energy, but they immediately stop. So basically a self-regulating or self-extinguishing nuclear reactor. You start the nuclear reaction, you create heat. The entire system expands a bit, the pressure goes down, the temperature goes down, the nuclear reaction stops until everything has settled down. The pressure is now so high that the temperature is sufficient that the Maxwell-Boltzmann distribution of this particle is shifted to where the tunnel probability is sizable and the Gamow window basically opens and you start again. Or brown dwarfs. Brown dwarfs will be very interesting what the James Webb Space Telescope brings us, how many of them are out there. Because of course they are very hard to observe. They are so cold that their Planck spectrum is mostly in the infrared. James Webb Space Telescope. So this will be very interesting again. And you have seen I spent now relatively, oh, by the way, here's also Rachel. Rachel, you remember Orion, bottom right, his bluish star, which will in the next couple of 100,000 years become reddish. Because it's still in the expanding phase to become a red supergiant. Okay, so then we have the last part of the Hedgepoing Russell. I think that the rest I have talked about, I hope so, is bottom here white dwarfs. And we later gonna see how these guys basically at some point get rid of the hydrogen envelope. And what is left is then maybe some carbon, maybe some oxygen, depends. So these small ones we don't know because they live too long, we can't observe what happens to them, but sun-like ones, they have the tendency at some point, carbon maybe, our sun might, yeah, it's now already going in advance, our sun might make it to oxygen burning, not high, because then the set, this Coulomb wall becomes too high. Even if the pressure in the center becomes hot, even if it becomes there warmer, Coulomb wall becomes so high that this is not sustainable. There we need then bigger masses. So this is obviously happening then later when the star leaves the main sequence. As long as the star is on this main sequence, we assume it's burning in its core hydrogen. This is the major fuel, it's the easiest one to burn. But then we think back, have you ever heard of helium, 2 protons? That has only 2 protons. Some of you might have heard of alpha particles, which is helium-4, 2 protons, 2 neutrons. Then there exists another one, helium-3, 2 protons, 1 neutron, but the neutron is not bound. If we bring 2 protons together, they stay together for maybe 10 to the minus 21 seconds. And then they say farewell. Extreme short. But nevertheless, we assume now we have basically these protons, that 2 protons merge and something is happening here. A proton, in the short time where they are together, one of these protons might say, oh, we could stay together if I would be a neutron. Then the entire system becomes energetically more favorable because proton-neutron is bound by 2.2 MeV, a bit more, but who cares about this bit more? And if you remember, the mass difference between proton and neutron was 1.2 MeV. What means if now one of these protons says, I become a neutron, the later on the bound system would have 1 MeV, an energy more bound or binding energy, which would become free as kinetic energy. Well, in this process, there must be, of course, we start here with a positive charge. Here we have a neutral charge, what means somewhere this positive charge needs to go. What happens in this process, there must be a positron form. This is the antiparticle of the electron. It's the same as the electron, except it has positive charge. It's the antiparticle. And if electron and positron meet, they form something like a hydrogen atom, circle around each other, give energy away, and at some point they come too close. And when they meet, particle, antiparticle, they annihilate. They cease to exist. And what happens to the energy stored in the rest mass becomes radiation. 2 quantums must be go back to back because of momentum conservation. Sometimes there are 3 quantums going away, but 2 characteristic quantums with 511 kilo electron volts. By the way, this is used in a PET scanner, PET scanner, positron emission tomography scanner. So if you suspected to have cancer, then you would get any sugar. Cancer method has a higher metabolism, what means the sugar enriches more in the cancer. Then one can scan where does the radiation come from, and if you see something, there is something where, yeah. Fortunately, it's not longer 50 years ago, but this was the sentence. Nowadays, you have the survival rate of 50, 60, 70%. So. Okay, but basically we use this annihilation radiation that then becomes free. We create then basically very hard light, this energy that corresponds to the rest mass of an electron, which was roughly half a mega electron volts, so 500,000 of electron volts. But obviously we have a problem. We need to bring this together. They need to tunnel together, what is already very unlikely. And then in the short time they stay together, the neutron has to say, basically do the inverse process, not decay like the free neutron to become a proton. What we have here now in this bound state, that the proton says, okay, I become a neutron and emit this positron and the neutrino. Ooh. And as I said, the 10 to the 21 seconds, minus 21 seconds. I don't even know what the prefix is. 10 to the minus 18 is ATO, but 10 to minus 21, I would have to look up. Very short. So the process is very, very unlikely. In fact, it's so unlikely even that we have relatively intense proton beams. I don't think that we ever created in a lab a deuteron, which is this proton-neutron bound hydrogen from 2 protons. So that means, how about the star? Why does it work in stars? If you do some experiments, even if you shoot a beam on candle wax, well, candle wax is always good to have a lot of hydrogen in because CH2, carbon hydrogen. Or water, you also H2O, so you have a lot of hydrogen. If you shoot no hydrogen in, at these energies that the star does it, this is the other thing. We have to consider that we do it at the energy where a star does it. I'm going to show you at some point nuclear reactions that have been measured that are for nuclear astrophysics. And you will see that this low energy tail, it's not possible. It takes far too long. And then when you wait a lot, or when you measure a long time, what happens, you always have background. So the background keeps on accumulation. At some point, even if you subtract the background, but you switch off your beam and measure at the same time just the background, then you subtract basically. Even then, occasionally the statistical fluctuations are so high that no signal. So hard to measure, but why does it work in the star? Well, it compensates for these low chances by buying so much tickets in the lottery. There is so much hydrogen gas around, the pressures are so high, what means the particle density is also very high. You create so many chances that at some point it will work. And obviously it works enough. Because our sun loses. What happens also in this process, there is then a bit of mass loss corresponding to this 2.2 MeV over c squared. So one could now calculate this back. This is 2.2. This is about 1/500th of a atomic mass unit, which means 1/6000 of a carbon, the mass of a carbon-12 atom. That is in this process transform from matter, from mass to become energy. Oh. In total, our sun burns away a couple of 100 tons per second. So it's quite effective, but in comparison to other stars like these big blue giants, it's relatively fuel efficient, to give you a bit of a feeling. Well, once we have this deuteron, then it's relatively nice and easy. So we have the deuteron, because 3 helium, 2 protons and 1 neutron is bound nucleus. It's even stable. That's brilliant. So we can easily capture another proton and get this 3 helium. And we have solved one of these massive problems, because you remember that shortly after the Big Bang, most of the neutrons were gone. But now we basically, in this process, we have recreated a neutron. Oof, lucky us. Well, then if we have the second chain that does so, what can happen is at some point that 2 of these 3 helium nuclei collide. Tunnel probability is now a quarter. The Coulomb wall is 4 times as high, what means the tunnel probability is now exponentially very, very down. But nevertheless, it happens in stars. And then we create from this 3 helium 2 protons, 2 free ones. So they are basically recycled. And then we have this 4 helium nucleus, which is an extremely tight bound system. It's because it's so nicely symmetric if you exchange protons with each other or neutrons with each other, or neutrons and protons, and it's very nice. Extremely tight bond nucleus, and then in this process we create about 17 mega electron volts in energy, or in the different steps and sum everything up. It's quite nice. But this is then in the core of the star, and of course needs to migrate somehow to the surface to be irradiated. Okay. So this is what one of the major processes. I will show you a few others later, but this is the major process that goes on in our sun, in every star on the main sequence. Okay, so and now we go to my playground, at least the low mass part of my playground. I usually play a bit more with the heavier ones. These light ones are a bit boring for me. They are too easy to understand. Okay, and what is my playground? Basically, we plot here the neutron number. We plot here the the proton number, what means the chemical element. Neutron, hydrogen, helium with 2, 3 protons, lithium, 4 beryllium. This is basically then going along the rows of the periodic table. So and then we have different stuff in here. We have this black stuff, these black boxes. So helium 4, 2, 2, which is stable. Everything that is black here is stable. This is when once created, it usually stays this way, except an alchemist that does some chemistry doesn't have a chance, but a nuclear physicist that has a nuclear or a particle accelerator has a chance to change them. So this is stable. And then we have other ones that are bound, what means these 2 protons, the 2 d protons, so 2, 0, you see here it's empty. This means this is not bound. We can bring them together. They stay for a very short time together and then say farewell to each other. The same is true for the d neutron. Or for hydrogen 5. So you see 1, 2, no, just the proton-neutron system. 3 hydrogen. Tritium. Then we have the 4 hydrogen, but this is where you need really to be good. By the know, what we could create was hydrogen 7 or hydrogen 8. Helium, we are also extremely, you see now helium 10 nucleus discovered at Riken. Riken is a radioactive beam factory in Japan. They are basically 10-15 years ahead of everyone. They create now these very exotic systems, which are occasionally stable and bound. Bound means you bring it together, they stay together. What happens is that it says, okay, we here now helium 8. Helium 8 says, we are bound, but we are 6 neutrons and only 2 protons. The nuclear force is strongest when there is an equal amount of protons and neutrons. You see that the stable ones go nicely along, where we have 5, 5, 6, 6, 7, 7, and maybe slightly here it tends already to have a bit of neutron excess, but goes nicely along this. So proton neutrons, obviously, they want to have equal amounts. And this can be reached by having transmutation of a neutron, for example, in this 8 helium, to become a proton. Then we are here at 8 lithium. We have now here 3 protons and 5. The natural thing would be this stuff decays again. 1 neutron to become a proton, then we have 4, 4. We would be at 8 beryllium, but now it turns out 8 beryllium lives for maybe 10 to the minus 17 seconds. And then it splits up into 2 4 helium nucleus. This is this nice, super symmetric and bound system. So this is then unbound. The others, the ones that are pink, are bound but radioactive, unstable, radioisotopes. But we can synthesize them and they stay for together. What happens is maybe a transmutation to become another element. But stuff like helium-13, lithium-13, which would be here, that is unbound. It immediately evaporates one of these neutrons, another of these neutrons, and then we have 11 lithium, which is just tiny, tiny, tiny bound. These are then really details of the nuclear force, but you have learned already that the nuclear force wants to have the same amount of neutrons as protons. Then what we also learn is that the nuclear force is short-ranged. Far shorter than the Coulomb. Coulomb force is infinite. So short range means you have only neighbors that talk to each other. This forms a bond in the community, and obviously a strong bond that keeps the community together. But then you have one guy at the end of the street which listens very loud with his stereo to crappy music. And then you have another guy on the other side. This loosens, of course, the binding, and the neighbors start now. This is the Coulomb force, the infinite force. And if you go to heavier and heavier, because they talk now always to each other, while nucleus are just the neighbors around. They talk to the neighbors. What happens if you go to heavier nuclei? We need more neutrons than protons. This is basically, here you see now 8, 8, but then we can have already 2 neutrons in excess. This is another thing of the nuclear force that will later become important. So, and here we see now, with these proton chains, well, we basically go up here, nicely along up to 4 helium. Okay. And then we have a problem. If we want to capture a proton, it doesn't work. Immediately dissociates. This is not bound. Even if it would work, decay here, not bound. Here, well, we could go with neutrons along, despite that we have no free neutrons. Not around. Doesn't work. So we have here this in the A equals 5 for mass number 5. There is no bound nucleus. Makes a barrier. The next is, okay, why not take 3 helium and 4 helium? Make 7 beryllium. Okay. Radioactive, we form 7 lithium. Nice. Aha. So we have now a chance to form a bit of lithium if they are extreme high density and high temperatures, like as after the Big Bang. But then we capture protons, and what happens? We are back down here. What a nuisance. So we have now start to have problems. We can also merge to hydrogen for helium. We had 6 lithium. Okay. Again, similar problems. What we do we will always end up at latest with this 8 beryllium. And 8 beryllium doesn't allow to be bound. What you have now, what you see here is what is called Beryllium Barrier. In fact, this can be nicely shown with the nuclear force. Why this is unbound? Well, what you see here is now the binding energy per nucleon, so per particle that we have in the nucleus. If we just plot it, every time we bring one, there's a certain amount we get. And this is almost linear, slightly bending down over a certain amount. This is when the Coulomb force comes into game. What we get here from about 20, we get a saturation. This would be nicely saturated. This is basically the short range. This is direct consequence. If not, then we would have the a's nucleon talking with A-1 nucleons, where A is the mass number. We would get a proportionality to A squared. If the nuclear force would be in very long range or long range, we would get much bigger nuclei. This is not possible. So this is basically what you see here is this binding energy per nucleon. The saturation effect, the short rangeness. And you see, of course, that Coulomb force, this is always binding loosening. Then we see here these effects like 4 helium is, for example, where we might a spike. Because of this symmetry, there comes a couple of very fine details of the nuclear force. And we see here we have 8 beryllium, which would be also a spike, but 4 helium is slightly more bound per nucleon. It's energetically favorable for 8 beryllium immediately to split up into these 2 4 helium nuclei, which I will in future call alpha particles. So-called alpha radiation. Oh. Yeah, that's nuisance. Once we make it, we see that the binding energy per nucleon in carbon-12 is again great. 6 in oxygen as well. So we see always if we put clusters of these alpha particles together in the moment, so basically we could now say some nuclei are built up like these clusters. This is the so-called cluster model. 2 of them. They touch only in a very narrow point, which is obviously not enough to hold them together. With 3, we have 3 of these touching points, which obviously cause a bit more binding energy. And with 4, we can make a nicely pyramid. This triangular shaped pyramids. Oh, so you understood basically now clustering in nuclei. And why is there this beryllium barrier? If we plot this here a bit more, the binding energy is always somehow negative. So a different way that we plot basically the nuclear masses. We see we have the lightest nuclei and renormalized for the mass number. The lightest one are the ones where most mass has been transferred to binding energy, the most tight bound. This is here in the iron nickel region, and we call this here the value of stability. If we extend my playground, again, neutron number, proton number, but now we go to really all along the periodic table. This here would be lead. This here is xenon, barium. This must be so krypton, or 50. This is krypton, strontium, zirconium. So you see this bend over of the value of stability because of this, the enhanced Coulomb effects for heavier nuclei. But in light nuclei, we have nicely this following the n equals z line. Okay. The important stuff for us was this beryllium barrier. What you also see here, it should be a bit more extended towards neutron-rich side, thanks to Riken. They are very good in synthesizing nuclei for the first time, at least for the first time man-made. So black is what is stable, what we find in nature. Blue is what we could somehow synthesize with nuclear reactions and then investigate. Later on, we will talk about what is called the R process, the rapid neutron capture process. This is the way how we think that elements beyond iron, what is somewhere here, all this stuff, how this has been created, at least 50% of it must come from this R process. So this is in my playground a bit shown to you. But we are now at the very beginning in the hydrogen burning. So we have seen these PP chains creating then us basically down here PP1 chains. Then we have these alternative chances, PP2, but you see 4 helium, 4 helium. Whatever we do, 8 beryllium, 4 helium, 4 helium. Whatever we do, we have a problem. So sometimes what happens if we have created such a positron, an electron nearby, this electron might moderate the transformation of the proton to the neutron easier while they are together. So if there is, for any strange reason, also electron, well, the star is a plasma, which means we have this soup of positive, negative charge particles, and for each proton we have also an electron around. This is sometimes moderated, and we get this process. So why doesn't the star collapse? Well, we have now this light pressure that is working against the outside. And obviously the light wants to travel randomly around because it's constantly scattered, but in the long term it will travel from the inside to the outside, from the source to where it's then emitted. Now, because the stuff is in there so dense, it can be estimated that it takes for one of these light particles that has been created in the center of the sun. Well, there is so often scattered, it undergoes this random walk. We can estimate it's 200,000 years between its creation and coming to the surface. And once at the surface, it comes to us. It takes another 8 minutes. Sometimes when life is crap and the sunshine, at least it's a sunny day, I like to go outside and have the sun shine a bit on my nose and then think about this light ray that came now, this photon, hit my nose and nicely makes it warm. What journey it has behind. And this sets all trouble that we have usually a bit in relation, and we are just a small part. In case you again or have one of these days where there is and there should be or deviating, then just calm down a few minutes and then go hopefully a bit more comforted back to work. So, but the interesting thing is that light takes a long. There's 200,000 years. There are other estimates which take a million years, but this is roughly the same order of magnitude. So if this really takes so long, how do we know? Because it has been so often scattered, and every scattering process changes a bit the light particle. So the one that comes out at the surface doesn't have much to do with the one that has been created here. So who tells us this is really true, what we think about the surface, about the center? If we would have stuff that basically the interaction probability is so low with all matter that it basically can pass directly through. Do you remember the neutrinos? These are two families of elementary particles, the quarks that build up the matter, and the leptons, what mean electron, muon, tauon, and each of them had basically its own neutrino. In all these reactions, neutrino created, neutrino created, neutrino created, neutrino created, neutrino created. A couple of neutrinos are created along these chains. Or at least here one. If you go this chain, also just one. Well, if you go down this chain, it's two. This pass, it's again two. So at least one per process. Every time a proton becomes a neutron. Stupid me. So now these neutrinos, why are they so difficult to detect? Why are we so ignorant towards them? Because they basically do not interact. They don't have charge. What they do, well, they are so light that even if they hit something, this is for when you play a cotton ball and throw it to an elephant. The only thing that could happen is that the elephant feels tickled. Otherwise, there is basically nothing happening. The same as with the neutrino. If it hits something, that you don't really get a signal out. The neutrino bounces off. It just changes direction. There might be a recoil, but then it's so few. As I said, the upper limit at the moment is 1.1 eV for the mass of the electron neutrino. We know 2 of the 3 neutrinos need to have mass, but at least 2 of the 3 need to have mass, because we know them need to have mass differences. And if we have 3, then 2 must have. Oh, yet we don't have a clue how big they are, except for the electron neutrino. We can say it is 1.1 eV. But because they basically do not interact, they whoosh. Takes them 2 seconds, but they're created. And if you give them a couple of kilo electron volts, they're so fast, the speed of light almost. So it takes then another 2 seconds to come out and another 8 minutes to travel to us. There are so many produced. If you take your fingernail, turn it towards the sun, every second about 200 million of them pass through your fingernail. Now, so many reactions in the sun. And what is the surface of the sphere? Coming from the center of the sun towards your fingernail, the distance squared, and then the surface area, and then you normalize for the square centimeter maybe for your fingernail. And you know how many reactions that go on in the sun each second. The problem is you can stand now for your rest of your lifetime, and if at all, there would be 1, if you're really lucky, it's 2 neutrinos that interact with your fingernail. So the interaction probability of them with matter is very, very low. Then you need very fast ones that they really give a push. Slow ones, but they're a bit of a nuisance. So these neutrinos, they are the answer. They let us see basically into the sun. But they need a certain speed in order to then induce a reactions that we can again measure. Because usually you need to overcome then some threshold. When you switch on the light, usually the switch has a bit of a resistance. You need to, and only if you. So there is a minimum threshold necessary, and you probably have all. We all had this is already defect switch where you needed to press like hell. Okay, so they make it instantaneously out, and the important stuff is these ones. They get sufficient amount of energy. So they get over a certain threshold that has then been used, because neutrinos from these reactions, what they can do, if we shoot them on 37 chloride, or chlorine, it has 18 or 17 protons, and then I would have to check. This is a stable isotope, one of the stable nuclei, but with a neutrino, we can now basically induce the same reaction, neutrino and chlorine to proton, to argon, we create another proton. This hits now a neutron. It changes this to become a proton. Then in order for neutral to positive charge, in order to have here then the charge neutrality, we need also to create a negative charge, which is this electron. Okay. This has been used, this reaction, in order to find it. And this has been done in the so-called homestake experiment. Because it's so unlikely process, you need to be away from every background that you can eliminate. And what on the surface of the Earth, we constantly get bombarded from cosmic rays. There's constantly something coming from the sun or from other stars even, and we constantly get bombarded. It was first assumed this was terrestrial, and then a guy put a Geiger counter or something in a balloon, let it go up, and he realized there's much more if the higher you are up. Cosmic rays. Well, there's also coming a bit out of the Earth, especially Scotland, lots of volcanic stuff. You constantly get radon gassing out. Nearby Loch, you find a pitch blende, what means uranium ore. There is always something. There's no zero radioactivity, but nevertheless, if you go very deep undermined, what you have is this rock above you. This shields you at least most of this cosmic radiation, except stuff that basically doesn't interact with matter, what means neutrino. Okay, and this is what is done in the so-called Davis campus. Well, there's also Ross campus, obviously an old mine. We go 1,000 meters down. The European lab, by the way, is in Transasso, which is in the Apennine in Italy. It's mountains that are still 1,500 meters, 2,000 meters high. And there is a motorway going through, and halfway through the mountain, there goes a tunnel right. This is the European Underground Lab, Transasso. And when I was a PhD, there were reports that a guy there was basically 1 or 2 months like living underground and just ate junk food, and then got scurvy, this disease that the seafarer usually got. Dangers of a physicist's life. Yet, so there's this homestake mine, which I think is in Dakota, but I'm not sure. So this is an underground to get rid of this cosmic radioactivity. And there was a big tank that contained 615 tons of C2CO4, whatever the chemical word is, I have no idea, which is usually used as dry cleaner. So you make this massive amount of dry cleaner and hope that the neutrino from the sun would change the chlorine to an argon. Argon is not a nice thing because it's noble gas. So immediately it doesn't want to react, it gases out. All you can suck it away from the surface and then bring it in front of your detector and see whether you get a radioactive decay that corresponds to the decay from argon back to chlorine, creating here this neutrino and then a positron. And the positron is also nice, so you get then the specific radiation from the chlorine after the decay. As well, you get this typical when positron electron meet is 2 times the rest mass quantums, or these 2 quantums where each carries the rest mass energy. If you have them within a certain time window, you can say, okay, there was something. And this was done by a guy called Ray Davis. That's why it's called nowadays the Davis campus. He did so for 30 years. For 30 years, he went there once a month. He went there to this mine to check everything is working properly and to read out the results and record them. So he got the Nobel Prize for his persistency, basically also showing that the neutrinos were there, and there are also this Koshiba, he is then a big boss of a Japanese experiment that makes it much better. We're going to talk in a few seconds about. So what Davis got was basically count rate per month, and this over, well, you see here now more than 20 years. No, the only thing was we expected basically to have there 8 reactions per month. What he got was, if we take all this average, the statistical fluctuation of small numbers, big fluctuations, if we have a small mean, but since we have a lot of data, we come down to 2.6, 2.66. Something like this. 8 and 2.66, how are they related? Exactly, this is the factor 3. So first of all, the worst thing in this scenario is simply our sun model is complete bollocks. It's done. This is one thing. But people quickly realized there's this factor 3, then remembered how many families of neutrinos are there. 3. That is already suspicious. So this here was long known as the so-called solar neutrino problem. When I was a student, it was still the solar neutrino problem. But this factor of 3 immediately triggered 3 neutrinos. How about the sun produces these electron neutrinos? But then when traveling to here, neutrinos have the ability to change their character from electron to mu neutrino, from electron to tau neutrino. What means you would lose basically 2/3 of your neutrinos that are capable to instigate this particular reaction. Well, and then this is the idea of neutrino oscillations. So basically, given a certain way to travel through matter, they start now to change their characters from electron to away and back to electron and away. And in the end, this was the idea, neutrino oscillations. Well, we have seen the Japanese lad, Mr. Masatoshi Koshiba. He was the boss of another mine experiment, but not landmine, it's mines in terms of mining ore or coal. This is the super Camioconda experiment. So this, what you see here, is a gigantic tank of high purity water. On the walls, you see these are called scintillator detectors, and they are capable to detect so-called Cherenkov light. Cherenkov light is when a high energetic neutrino hits an electron or a proton and gives it such a pulse or momentum. It starts now to race through the other matter, and while it does so, it interacts with the other stuff, and you get light. And this light forms something like a supersonic cone. So then when your detectors fire on both sides or on all sides, you can recreate the trace. You get even where this charged particle was racing to, and since momentum transfer in a two-body process is usually, one could at least go back towards a cone where this neutrino comes from. So, or we get at least the direction. Does it come from the top, from directly atmosphere above, or does it come from the bottom? What means it was once going through the entire Earth. Well, by the way, what you see here then on the right-hand side, this is a rubber boat with 3 technicians of average Japanese size, or I think they are average size. Of course, they are sitting. And what they do is they maintain at the moment the detectors. So occasionally there are 1 or breaks, and then you need to change it. What means you need to pump this high purity water to the other tank until a level that you can work. Change the detector, Fox comes out, and then you basically raise again the water level, and you're back in business. So now what Super Camioconda did was basically use neutrinos that are created in the upper layer of the atmosphere. And then because of this sensitivity of the direction where it comes from, it could now basically confirm that neutrinos transmute to electron or tau neutrinos, that they really oscillate away. Then they could get the oscillation length, because you have know how much matter was there in between, or where was the stuff created. Therefore, the solar neutrino problem was solved. And we are relatively sure that the model about the hydrogen burning in the core of our sun is correct. So, neutrino astronomy, the first time really done here. Nowadays, it's an opening field that starts to emerge. For example, if you hear about the IceCube project, for me, of course, 2014, a research project that I have led got elected as one of the top 10 breakthroughs in 2013. But the most important one was then voted to be Ernie and Bert, which were 2 absolute super high energy neutrinos that were observed by this IceCube project. And what they do, it's at the South Pole. They use a cubic kilometer of ice as detector material. This ice is so pressed that it's basically blue and light can travel through. Well, if there's something happens, the light can travel, and then have strategically placed their detectors inside this ice. In order to get a detector in the ice, what you do is basically you dig a hole with hot water, pouring hot water in. until you're at the depth you want, and place the detector in, put cold water on top, and at some point. So this emerging field, neutrino astronomy. 2 years ago, there was this ANITA, anomalous neutrino events with eta electron volts neutrinos, which is about 4 or 5 orders of magnitude more than the LHC gives us. 2 neutrinos or 3 neutrino events that were so high in energy, we have no clue where they come from. It must be within 150 million light years, because neutrinos, when they fly through the space, what do they see? Every cubic centimeter has this 400 photons of the cosmic microwave background. Photons momentum is then usually proportional towards the photon energy, which is not much. Therefore, the momentum transfer is there, negligible, as long as you are not traveling with almost the speed of light, or very, very fast. Because then, if we transform from the rest frame of the lab to the rest frame of the traveling particle, these photons have suddenly massive energies, and therefore momentum transfers. It means they slow you down. You basically are traveling through this tube of photons that is a bit jammy, or quicksand of built by these light particles. So enough fancy stuff. Back to our sun. So basically what our sun has this core, hydrogen burning, and the rest is basically inert shell. Of course, then you burn the hydrogen to helium, but helium doesn't burn. Helium is heavier. What happens with the heavy stuff? That is, of course, slowly but surely. This is when you no, that's the wrong example. The heavy stuff will slowly but surely migrate towards the center and form there enriched helium core that is very likely not burning anymore. But in the shell around, we still have this hydrogen burning. And burn basically this helium. But now we have seen the problem. If we bring 2,4 helium nuclei together, we get 8 beryllium. We are in the beryllium barrier. We have seen this before. 6.7 10 to the minus 17 seconds. That is not a long time. This is even for me relatively fast. That is faster than the no. Yeah, that is no. I've lifetime measured that is shorter. So my personal record is a bit faster, but this is still extremely fast. That is the case. Well, the logical idea would be to say, if this with the proton works, because there's such a high density, so even the process is unlikely, there might be that now this third helium comes along, while a beryllium is just there. Of course, the tunnel probability, we have now 4 times 2, 8 times as high Coulomb wall. That means the tail then becomes, you need higher temperature. Then also tunnel probability, there enters the mass exponential. The higher the mass, e to the power of minus the mass. So that's the reason, by the way, why you can try as often as you want with as many cars as you want and try to drive through a wall, because that's why it won't work, because then the probability is effectively 0. But now, of course, the particles get heavier and heavier. This strikes a bit, and again, the tunnel probability drops. What means we need now higher temperatures in order that such a process can go on. How can this happen? Well, we have now this higher mass in the center, which already creates a bit more gravity. More gravity means it also becomes a bit hotter, more pressure, more stuff becomes hotter. Simple as it. Yet the interesting thing, even if we consider there, play a bit around with the temperature and lift it so that the Maxwell-Boltzmann distribution is again going towards the higher tunnel probability, the gamma peak becomes size, all this kind of stuff, it doesn't work out. With the energies that we have there available in the sun then later, will kick in the sun in so 3-4 billion years. In heavier stars, it's already, of course, going on. Obviously, we consist of carbon. There must have somehow carbon must be produced, and it is this process. But if we just look into the normal cross section, it's not enough. So if we would take this picture from before, we have basically our Maxwell-Boltzmann distribution, the tunnel probability, and the energy goes now to the top. So we would now build our gamma window or gamma peak. Doesn't work. It's not enough to create carbon. And this led Fred Hoyle, who was then later an outcast because he was always fighting against the Big Bang and came then along. Every time there was a new experimental finding, he came along with an obscure explanation, and he got himself more and more in the offside. Many people also didn't want to have anything to do. So basically, you are now discredited. You are no longer my friend. That is also horrible. Except the great Richard Feynman. He always said physics is one thing we can discuss, but he's still my friend. What I think is a great virtue to stay with your friends. Of course, you can tell them you do nonsense at the moment, but still not change your friends because the others say so. Okay, so well, and Fred Hoyle, for this what comes now, should have got a Nobel Prize, because what he said at the mass difference, the energy that corresponds just to the mass difference between carbon-12, which is obviously tighter bound, and therefore lower, and 8 beryllium plus alpha, that must be. So if we binding energies transform them to mass, it's about 7 MeV. And Fred Hoyle said just above there must be a 0+ state, because what happens in the quantum mechanical tunneling, if the system that is formed has there an excited state at just this energy where the particle is incident, or would then afterwards be, after it tunnels through, the tunnel probability is drastically enhanced. This is called the resonance enhancement of the tunneling. And that led Fred Hoyle to propose. So basically we would get now here this tunnel probability every time the energy corresponds to an excited state. And what comes in into game, angular momentum, what means the reaction mechanism that plays in a role to enhance this. Then the lifetime of a level, lifetime Fourier exponential decay, Fourier transformed, results to what is called uncertainty in energy, a width in energy. The shorter the lifetime, the wider is this peak. So if we have such a thing, the gamma window here is obviously drastically enhanced. So we would get here this spike in the reaction rate on top. And it turns out, if one does nuclear structure physics, that carbon-12 has this excited 0+ state just in the right energy. If this wouldn't be there, there would be almost no carbon nowadays in the universe. Would be the evolution of every heavier star would be completely different. It would be simply cease to burn. There would be loads of helium in the core. There would be loads of unburned hydrogen, and probably the direct collapse to a black hole. No life. If this would be a bit above, the reaction rate would again be too low. If it would be below it, that wouldn't work at all, or just briefly. Then we still have a tail of this peak coming over, but so it's just at the perfect. If it would be a bit too low, that would maybe too fast burning. We're so lucky. Well, but nevertheless, we form now in this what is called the triple alpha process that we need to jump over the beryllium barrier. So this triple alpha process we form in this very unlikely process that this happens, that we form this 0+ state, this excited 0+ state in carbon, which we call the Hoyle state. This is the only nuclear level which is named after a guy who predicted him. Oh, very special stuff. So it's the Hoyle state. And to our shame, up to about 2010, we didn't really know much about the structure of this Hoyle state. From now, we know it's a quantum mechanical superposition. Maybe now it works. A linear combination of two states. And one of these states is a linear chain of these 3 alpha particles. And one is 2 alpha particles and one in the center. So basically, this carbon-12. And they are superposition, and the resulting looks a bit like a golf club. So 2 in a row, and then the third one a bit off. This was the thanks to the efforts of Martin Freer in Birmingham. Martin did an enormous job. Yet this Hoyle state is there. 2 years ago, I would have said, nevertheless, we have this unlikely process, and then we have managed to form it. And now, if we have 10,000 times this state formed, it's still unbound. 9,000. 2 years ago, I would have said 9,997 times. 9,900 from 1,000. 99997. So 3 out of 10,000 would have managed that somehow the nucleus stabilizes itself by the emission of a gamma ray down here, or of very special radiation electrons down here. Except a year ago, Tibor Kibedi from Australian National University, he remeasured basically what we call branching ratio. And now it's from, I think it's 1,000 times, and it's 10,000 times, and it's 9,996 times. That basically we get the splitting up again. And only 4 times it forms, then we're really carbon-12. I'm not religious, but this is such a narrow bottleneck where things need to go through, that everything works just out that we can be here. Even I start now to think whether there is something behind. So this is the Hoyle state, and this allows for just enough carbon to be produced. By the way, Tibor, see, here we go. An old photograph. If you see, this is over here is the university, is the library And here we face basically all towards D block underneath the main entrance, the coffee area. And if you go downstairs, so this is a couple of famous guys. You see Dave O'Donnell, former UWS students, Paolo Sassarini, who does no PhD, with this guy here on the right. Hopefully you see the mouse pointer. This is Jacek Dobachevsky, one of the gods of theory. And then if we go here to the left, this here is Thibaut Kibedi. So he knows about Paisley. He was here about 2 years ago and then already told us about what is the consequence. Well, once the star has reached the helium burning, it basically goes 25–30% faster. By the way, the guy here towards the right, this is Vitek Nazarevich, who is the scientific director of EFRIB, which is the factory for radioactive ion beams. So $1.5 billion project. So now what do we do? Basically, we burn this helium in the very center of the star. Only there we have enough temperature, pressure, and therefore enough temperature to allow for the tunneling process to become carbon. That is already something. That's about what our sun will certainly at the very, very end of its life produce more carbon. Well, it starts already, but this is very, 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 very traces. But these traces have consequences. So slightly but surely, even in our sun, in the core, carbon already starts a bit more to enrich. So we have no carbon produced. And the star will, of course, we get the carbon ash that is not burning because it's not hot enough. We have this helium burning shell. Hydrogen maybe is still burning, but a bit of a shell. So then we have most of the star is basically this non-burning envelope. Of course, then the next thing is here we have carbon, we also want oxygen, and we want nitrogen. And now it turns out a very efficient mechanism to create nitrogen is the so-called Cno cycle. We have a reaction where carbon captures basically a proton. 6 times 1. This is even more likely than the two of these helium nuclei to form 8 beryllium, and far more likely than, or more likely than this third alpha particle tunneling to the beryllium. So this is even there more likely. So if you have carbon around, what can happen is this occasionally captures this proton. You get nitrogen-13, fine. Nitrogen-13 is radioactive, becomes carbon-13. This is stable. But this can again capture a proton. So we get nitrogen-14, which is stable. Nice. We have produced nitrogen. So the next is, this can again capture a proton. We get oxygen-15, which is radioactive, and becomes nitrogen-15. Nitrogen-15 can now capture again a proton. But it will capture the proton in such a state of oxygen-16 that we form, that this rather splits up again. So this is some kind of nuclear state that's rather built up of clusters. But this capture state is again one of these naughty, nasty, whatever ones that immediately leads to dissociation in carbon-12. So we have basically our stuff from the beginning back. This is just a catalysator. And we get 4 helium. The same as we would have in this process with this unlikely stuff The two protons meet each other, and one says, I want rather to be a neutron. That's from the very beginning. So this here is a bit more likely. But of course, before you can start this, you need to have carbon. And carbon you need to burn via these stages before. So this works then better in a second, third generation star where you have already bit carbon, or in later burning stages of a first generation star, or even second, third generation when you enhance them more and more carbon. Then you get this, what is called the Cno cycle, which has been predicted again by Hans Bethe and Carl Friedrich von Weizsäcker. Well, why I'm so fond of them, Bethe is from Strasbourg, which is just across the border where I grew up, and then Weizsäcker is also from the area. Oh. By the way, the Weizsäcker family is one of these families that constantly appears in different positions, in higher up positions. And, so essentially, we have no carbon working as catalyst for this proton to helium reaction. Works better, produces the same amount, but a bit faster. That means the more and more carbon you have, the better and better it burns, the more and more energy produces the star. Now, of course, in the sun, slightly but surely, we enrich a bit carbon already. The Cno cycle becomes more and more important. At the moment, it contributes 2%, but it's certainly going to rise. And then in 1.5 to 2 billion years, it makes basically the sun so hot that, farewell any ocean. Probably it's then better to settle over somewhere. Like in 2 billion years, what do I care? Don't want to know. Probably my football club has then managed to 200 million times to get promoted and relegated or whatever. But this is something I care far more. Okay, so this is basically one of the side cycles. But then we have also seen we want to go now from carbon to oxygen, and oxygen doesn't work out here. So what we need there is a direct reaction, alpha particle, so this helium, plus carbon-12. This is somehow the holy grail of nuclear astrophysics. To get this cross-sections or probabilities, cross-section is a measure for probabilities at the energies where a star burns it, to get this right. Oh. This leads then to the so-called helium burning. But I would say I stop now. This video is probably already far too long. Sorry about this. This is, of course, my own turf, and then one starts waffling and never ends. So I stop now, and the rest should be then 20 minutes or so. Watch it in a separate video. So also coffee is running short. See you then in the next video.